In today's video, the third chapter of our Rust series, we're going to be covering variables immutability, data types, functions, comments, and finally control flow. Additionally, I'll be showing off one thing in this video that I think is really going to help us to learn Rust in a much more dynamic way than we've been doing so far. I'm excited to see what this chapter holds, so let's get started. So the first thing this chapter wants us to do is to reinforce that variables by default in Rust are not mutable. So we'll create a new project using cargo called variables. And inside variables, we'll open up source main.rf, and then we'll replace the current contents of this file with what we see on the right hand of the screen. Okay, we'll save that. And when we try to use cargo to run it, we should see compilation error telling us that we can't assign twice to an immutable variable. Again, I like that the error messages that we see here outline exactly where to identify the issue. So with that, let's fix the problem by making x mutable, and then we'll save it and use cargo to run it again. And here we see it changes the value correctly. Okay, and it's already time for our first quiz. Let's jump in. So the first question is, which statement best describes what it means if a variable x is immutable? And our options are x cannot be changed after being assigned a value, x is stored in the immutable region of memory, you cannot create a reference to x, or after being defined, x can be changed at most once. Well, I'm pretty sure one is correct, but let's reason out the rest. It being stored in immutable region of memory isn't something that Rust has explicitly talked about yet in this book, so I'm going to guess that that is no. Us being able to create a reference to x definitely isn't true. And then after being defined, it can only be changed at most once is definitely not true, as we saw above. When we tried to change it a single time, it failed. So I'm going to guess that the first answer is correct. Okay, we have a freeform response for this next one. What is the keyword used after let to indicate that a variable can be mutated? And the answer here should be mut, M-U-T. Question 3, determine whether the program will pass the compiler. If it passes, write the expected output of the program if it were executed. So if we look here, we see that it creates an immutable variable x, giving it the value of 1. Then it prints x, and then it tries to increment the value of x by 1. So this should not compile because x isn't mutable. Let's check our answers. Okay, first, second, and third answers are correct. Nice. Let's move on. Now this next section, it covers constants. Now I've highlighted a few areas that are especially important about constants, especially if you're coming from the world of Python. The first thing here is that constants aren't just immutable by default, they're always immutable. So in Python, constants are more so just a naming convention, where it's understood that you don't modify them, but there's nothing really stopping you from modifying them. The same is not true with Rust. And it looks like you can't even define a mutable constant anyway. Also, the type of the value has to be annotated when you define a constant. It's not something that can be inferred by the output of some expression. And speaking of expressions, constants can only be set to a constant expression, which they do have a reference down here linked that talks all about the different rules for constant evaluations, including what counts as a constant expression, constant context, and constant functions. So you can read more about that if you like. Additionally, based on this last line I highlighted here about the compiler being able to evaluate a limited set of these operations at compile time, it seems like Rust is actually calculating the value of the constant at compile time and baking that into the constant itself. So it doesn't have to evaluate things at runtime. And then it gives us an example here of us defining a constant. And for this, I want to show off something that I found. Because if you're familiar with my Python videos, you know I'm a fan of IPython, which in my opinion is a better version of Python's built-in REPL. Well, I was wanting to know if there's something similar in Rust, and I did find something that I think is going to suit our needs well. And even though my alias for this is called iRust, it's actually a tool named EVCXR, which I'm never going to remember it by that. So I just aliased it to iRust. iRust is apparently another version of a REPL, but from what I've seen, it's not as feature complete, and support for it may be touch and go. So I'll have a link to the EVCXR repo in the description so you can install it yourself. But for now, anytime that I type iRust, you'll know what's going on. And we're presented with this prompt here. Pretty nice. So what we can do is we can paste in that expression that we see on the right hand side, and we can create that constant ourselves. And now we have this constant available. And if we try to assign to it, let's see what happens. So we'll change it to something like 15. And here we go. We even get a nice error message that we'd see from the Rust compiler, telling us that we can't assign to this expression. And specifically that the left-hand side of the assignment is incorrect. Most likely meaning that there's a constant on the left-hand side of the expression. And in case you're curious, to get out of this, we type :quit. And now we're out. Okay, now moving down to shadowing, we saw a bit of this before. It was basically when we reused the same variable name, but storing a different value in it. But it also looks like there's a bit more to this, because it looks like we can create arbitrary inner scopes by nesting it with curly brackets. So let's actually test this out by creating a new variable called myvar, setting it equal to a string test. Now we have myvar here, which has the correct value. And let's create an arbitrary inner scope here and try to redefine for this myvar equal to changed, and then we'll print that out. And when we execute that, we see it prints out changed. It also gave us the result of that expression. But if we look back at myvar, we see outside that arbitrarily nested scope, it's back to test. Let's also see if this works if we want to change the type in this new scope. And it works. How about changing the type on the same scope? That worked as well. However, we lost the original value of myvar. And as they point out here, this is a different behavior than we'd see from mutable variables, because mutable variables have to stick to the same type. So if we create a mutable variable another and assign it to the string fresh, we have another. But if we try to change the value of another to a different type, say again 5, we have that mismatched type. But as long as the types are the same for mutable variables, we should be good to go. So remember, if the type is the same, you can use mutable variables. If the type needs to be different, then use shadowing. Okay, let's look at this quiz. 2 questions. Determine whether this program will pass the compiler. If it passes, write the expected output of the program if it were executed. We have a mutable variable x, assign the value 1, and we have an inner scope with another x, which it looks like it's trying to get the value of the outer scoped x. Interesting. I'm not sure if we've covered this yet with scoping and closures, but I'm going to guess if it's similar to similar languages that it does compile. This could be wrong. And then it would increment the value by 1, giving us 3. Well, we'll see if that's the truth. For question 2, we have to check to see if this program will pass the compiler. So it's defining a mutable variable x, assigning it to the value of 1, and then trying to reassign x to the string hello world, which as we saw on the left here, should not compile. Let's see what we got. So our first answer for number 1 was that it does compile, but the output of it is incorrect. Interesting, let's try this out. Oh, I'm being silly. I'm completely losing track of scopes here. The scope of this value change should end once we end the code scope here. That should revert back to its previous value of 1. Before we retry the quiz, we did get the second one correct. It does not compile. Let's retry that. It does compile. Should now be 1, and we got that correct now. Good. All right, let's move on. Let's spend a bit of time talking about data types. One thing I really like about Rust is that the compiler tries to infer the type as much as possible. We've seen this so far a number of times when we've created variables, either directly assigning a value to it or having the value be the output of some expression, and us not needing to explicitly assign a type. Now, there are cases where you do have to assign a type, like what we saw in our guessing game example, because the parse method was able to parse it into more than one output type. So when we created the guess variable here, we told Rust that we wanted it to be an unsigned 32-bit integer. So the first group of types we're going to get into today are scalar types, which represent a single value. And the first of these, which is common to pretty much anyone who has done some level of programming in the past, are integers. So I'm not going to spend a lot of time on these basic scalar types, but I will point out a few interesting things. So not only does Rust have a good selection of different sized integers here, even between signed and unsigned, but they also have an architecture-based size known as isize and usize, being the signed and unsigned architecture-based size. And what this means is it's going to use the size that corresponds to your system's architecture. For most of us watching this video, including myself, that's going to be a 64-bit architecture. And then the default that Rust uses is an i32, which is a signed 32-bit integer. One final note about integers here is how Rust handles overflows. And this is something that's different between a lot of different languages. For some languages, when you overflow, it starts to write into adjacent memory. Obviously not ideal. For other languages like Python, when you start to overflow an initial value, it just allocates more memory, so you can just keep increasing the size. But for Rust, by default, it implements what's known as 2 complement wrapping. So when you hit the upper limit of your integer size, it will wrap back down to 0 and then start increasing from that point on. The way you may want to visualize this is in old school games, where your character is going along, heading to the right side of the screen, and once it reaches the right edge of the screen, it all of a sudden pops back up on the left side, and then continues moving to the right again. It looks like we can also specify different behaviors if we don't want it to perform that wrapping, so it might be something that we play around with at a later date. Floats in Rust are pretty simple. We have a 32-bit float and a 64-bit float. They have roughly the same performance, however, the 64-bit float does have better precision. Now at this point they do talk about basic numeric operations, and most of these will behave the same as you would likely expect. Add adds, multiply multiplies. However, one thing that might be different is the way that division is handled, especially if you're coming from Python. So if we look at Python here, and we had 2 integers, 5 divided by 3, and we were to run that, we would see a float come out, 1.6 repeating. If you do the same thing in Rust, say 5 divided by 3, we get 1. So what Rust is doing is it will cut off the remainder and just give you whatever the integer portion of that is. In Python, we can do this with our floor division. So we would use double divide signs, and there we go. This may not be much of a surprise, but booleans are the same in Rust as they are for most languages, just being true or false. Moving on to character types, we do have a distinction between characters in Rust and strings. And one of these distinctions is also in the syntax for creating them. We see here that if we create a new variable c and assign it to single quotes around z, we have a character. However, to create the equivalent string, we would use double quotes. We now have a string. Now both are z. However, if we were to check that c is equal to s, we get a complaint about the mismatched types. We see that c is a character and that s is a string. So while you may be able to choose between the two in the language that you're coming from, like us in Python, it's not the case in Rust. Single quotes for characters, double quotes for strings. Now, moving on to compound types, which can hold multiple values, the first we're going to talk about are tuples. Now, tuples in Rust do have some familiar as well as some newer behaviors. So of the familiar, we have tuples will be fixed length once they're created. Also, the type annotations for tuples are optional. So if we were to create this tuple here, we have that tuple. But we could also do the same by getting rid of the type annotations, and we have the same thing. Now, I am glad that Rust did bring what they call destructuring to tuples as well, or what I call in Python unpacking, because I think that behavior is really nice to have. So in the examples that they give us, we create 3 new variables on the left-hand side, which correspond to the 3 values in the tuple that we just created. Now, if we look at the value of each of these, we see that it unpacked or destructured each of the values in that first tuple into their positional equivalents on the left-hand side of the assignment, which I'm really glad they added that. One thing that I do think is neat about tuples in Rust is that we can use dotted notation to access values at a specific index. So if we look at our tuple before, we see that it has 3 elements. If we were to try to check out the first of them, which is 0 indexed, we'd say tup.0, and we get the first value. Same thing for the second value, as well as the third. So we get nice dotted access for that, which I think is kind of neat. And the final thing about tuples is that an empty tuple is known as a unit, is that because expressions implicitly return the unit value. The equivalent of this in Python would be functions implicitly returning none. So it seems like an empty tuple or unit is the Rust equivalent of none in Python. And then finally, let's talk about arrays. So just like in most other languages, arrays can hold multiple values, but every value in an array has to be the same type. This is actually a common misconception in Python, is that people call Python lists arrays, but they're actually not. They're a distinct thing in and of themselves because they can hold multiple types. There's also a distinction in Rust and where memory lives for arrays. Arrays keeping their memory on the stack instead of the heap. And then another note is that since arrays aren't as flexible as vectors, they say that if you're unsure of whether or not you want to use an array or a vector, you should probably use a vector. Though it looks like we're not going to experience them to any real extent until chapter 8. And then we can see the syntax for creating arrays is pretty standard. One difference here is the syntax that we see on this line here, where we're creating a new array, A, telling it that each element of the array must be a signed 32-bit integer, and the length of the array is equal to 5. Now we have A. Of course, the annotation part of this is optional. Just like it was for tuples, we can create an array just fine, even without it. But there is an alternate constructor for arrays, which I think is going to come in handy, which is to create an array with a series of default values in them. So if we create a second array called A2, on the right hand side of that, we're going to use the array syntax here. And the first argument is going to be the value that we want filled in the array. For this example, we'll say 5, and we want there to be 8 values within the array. Now, if we look at A2, we see, yep, the array was created and it has 8 5s within it. So this is pretty nice for array initialization. Now, unlike tuples, arrays do not give us dotted access to their elements. If we try A2.3, we get an error there. So we have to use the typical notation here using square brackets. Kind of a weird behavior between the two. I'm not sure how I feel about that right now, but maybe as you use the language more, I may find myself agreeing with the authors more. And of course, like most other compound types, if you try to access an element that's outside of the length, then you're going to get an error. Okay, let's talk about functions. Now, we've already defined a few functions, but those are pretty much all lived in the main function itself. Defining other functions seem to be similar to other languages you may be used to. And one thing I like about Rust is that they do use snake case, all lowercase with an underscore between distinct words, which you can see here. A neat thing that I do like here in Rust is that they say it doesn't matter where you define your functions, only that they're defined in the same scope, so you don't have to worry about ordering of functions, which I think is really handy because some languages are picky about the order in which you define functions. Defining parameters is pretty straightforward. The major difference between that and Python is that types are required in Rust. In fact, this is one of the few areas where types actually are required in Rust. And one of the reasons why is that Rust uses the type annotations in these function definitions to infer types when you're using functions, specifically passing arguments in and getting values out. So it's pretty simple. Let's look at this print labeled measurement function. We see it has two parameters, value and unit label. Value being a 32-bit signed integer and unit label being a character. And of course, each of these is separated by a comma. Pretty familiar. Nice. And we're already to our first quiz. The question being, the keyword for declaring a new function in Rust is, and that should be fn, which is short for function. And then we got to determine if this code compiles. And I don't think it will, because they're defining function f, but there's no type annotated for what x should be. So I'm going to say it does not compile. And we're correct with both. Nice. Then let's move on to statements and expressions. So they say that function bodies are made up of a series of statements and optionally ending in an expression. More specifically, that Rust itself is an expression-based language. And the distinction between these two are that statements perform some sort of action, but they don't return a value. Whereas expressions do return some kind of value. We can test this out with iRust here. Instead of going through the effort of compiling that example there, let's run let y is equal to 6. and we don't get anything out of it. And as a result, since nothing comes out of that statement, we can't assign that non-existent result to some other variable. So in the next example they give, they're demonstrating this by saying let x is equal to the result of the statement let y be equal to 6. So if we try to run this, we should get an error. And yep, there we go. And in this last part here, they're touching on something that I think is going to be really important for the language moving forward, which is that those code blocks that we were messing with earlier are themselves expressions. And whether or not we return something from a code block, you can either change it from an expression into a statement. So if we look at a simple example here, where we have let x equal to 3, and that with a semicolon, because it's a statement, and then we have x plus 1, and we don't end that with a semicolon, making it an expression that's going to end this code bracket we see. The result of this code block is 4, being the result of the last expression within it. However, if you were to modify that and put a semicolon at the end, that's going to make the last part of this code block an expression and change the return type to an empty tuple, or what we learned earlier was a unit. And it looks like that's going to be really important when it comes to functions with return values. Because remember, with every function, we're creating a code block. And they say that the return value of a function is synonymous with the value of the final expression. So let's play around with this a little bit, and let's modify this example above. So we know by default that integers in Rust are a signed 32-bit integer. So the return type for this will be i32. So if we create that function, we should be able to call it perfectly fine. What if we were to modify this though? So instead of being i32, we make it an unsigned 8-bit integer. Okay, it didn't complain that time. I think what it's doing is it's modifying the type that we're creating x here, so it can fit into a unsigned 8-bit integer here. I think we can test that by explicitly saying that x should be a signed 32-bit integer and see what happens. Yeah, here we go. We now have a mix of return types. So there's definitely a bit of type inference going on with the code that you define in Rust functions. So I think it's a bit nice when it's flexible there, but it's still smart enough to check things like return types when you're explicitly violating your own function definitions. And then for functions that end in a statement, like we have with this printline function here, you don't need to specify a return type because it returns that empty tuple or that unit. I'm sure that if we were to modify this function one more time, so it ends in a statement, we'll likely get another complaint. Yeah, there we go. One other thing they talked about in this section that we really didn't get to see much is that you can return early from a function just like you would in Python by using the return expression. Okay, let's move on to the quiz. Okay, and the first question is that in Rust, a curly brace block like this, and it looks like it's kind of moving ahead of itself because I think these are Rust comments, is 1, an expression, 2, a statement, or 3, a syntactic scope. So the block itself is an expression and it does create a new level of scope. And we definitely don't have an option for all 3 because I think technically if you terminate it with a semicolon, it would result in a statement, but I think it's still an expression. So I'm going to say 1 and 3 here, and we'll see if that's correct. Then for question 2, we have to determine if this program will pass the compiler. And if it does, we have to determine the expected output if it were to be executed. So it defines 2 functions. The first being x, which takes in a signed 32-bit integer and returns a signed 32-bit integer by returning that number plus 1. It doesn't end in a semicolon, so we know that it is an expression that's going to return its value. We then have our main function here, which is doing something we haven't seen before, where it's using the println macro, but it's calling that f function and passing in the result of this expression, where we're creating a y variable, incrementing the value by 1, and the result of that expression gets passed into x here. So I'm going to say that it does compile, so I'm going to guess that Rust can infer the type needed in this let here, because it's being used in this f function up here. So we're going to start with 1, increase by 1, giving us 2, and then finally increase by 1 again, giving us 3. And we'll see if that's correct. Okay, so we're correct on 1. That's good. It is an expression and a syntactic scope. And then we're correct on 2 as well. Not too bad. Okay, let's move on. Okay, the next very short section is about comments in Rust, which it looks like for general comments, it's just 2 forward slashes. And these can be either on their own line or they can be at the end of some line. So yeah, it looks like they work pretty close to comments from other languages. There's no quiz on this, so let's push into the last section, which is all about control flow, which is crucial for pretty much any language. What they want us to start with is to create a new project with cargo called branches. We'll move into that and open up the source file and then modify it to be what we see on the screen. And there we go. We have our if-else block, which is a pretty simple check to see if the number that we created first, which is equal to 3, is less than 5. And depending on the outcome, which we know is true, we'll say the condition was true or the condition was false. So the syntax here looks pretty similar to a lot of other languages where we have our conditional check, and then we have an actual block of code here that will execute if the condition is true. Else, if it's not true, then we'll execute a different block of code, which has a typo in it. Okay, let's save it and run it. And we see that the condition was true. Pretty easy. And then if we were to modify and change the value of number to something higher, say 10, save it, run it again, we see the condition was false. Now, one important thing here, especially if you're coming from Python, is that the result of these conditional checks must be a Boolean, meaning it has to be literally true or literally false. In Python, we have the concept of truthiness or falsiness. That's not going to fly here. So make sure you're crafting your conditional checks in a way that is literally true or literally false. And the example they give below is something that would work in Python, but does not work in Rust. And the way that we chain multiple of these checks is with else if. So literally else and then another if. Now, luckily, one thing that the language does let us do is to do inline assignments using conditionals. So for the example they give, they create a condition, set it equal to true, and then for a number, if the condition is true, which it currently is, we'll get the output of this code block here, which will be the integer 5. Else, we'd get the output of this code block here being 6. Notice that these two are code blocks right here, and they do end in an expression, not a statement. So for the happy path example we have numbers equal to 5. If we were to change condition to false, run that again, number would be equal to 6. And if we were to try to change this from an expression to a statement, yeah, it's going to complain there. One other thing that it's going to complain about here is if we don't have the same type for the output of both of these code blocks. So right now, these are both the default integers, but if we were to change one of these to a string, we get an error. So they have to be the same type for this to work. Okay, let's start the quiz. First question being true, false. Executing these two pieces of code results in the same value for x. The first snippet saying let x be equal to the result of if condition 1, else 2, and the second one being let x, which isn't a thing that we've seen before, just saying let x, and finally these here. Luckily they do give us a nice little help here saying that both compile, so let's actually try let x by itself, which it doesn't seem to work with iRust, maybe because we also need that inline if condition. Still no, so it might compile in an actual file, but iRust doesn't like that. Okay, but logically though, the checks are the same if condition, so logically I believe these are equivalent. And then I actually had an idea just now as we started the second question for the previous example that I gave, and I tested it out and it did actually work. So the problem up here is that those two statements weren't equivalent because it didn't actually say x is equal to 1 within the code blocks or x is equal to 2. So this was an invalid statement altogether, of course. But if you do include x is equal to 1 and x is equal to 2, it does compile correctly, giving us the correct value of x. So moving on to this one, question 2 is a question to see if it will compile, and if so, what's the value? So we have first line here, let x is equal to 1, which is fine, and then let y be equal to the result of if x, and that's going to be a problem because x isn't literally true or literally false. So I'm going to say it does not compile. Okay, we got the first question correct and the second question. Okay, let's move on to looping. So we already did a bit with looping in our last video where we had our main game loop, and the default loop behavior here is an infinite loop. So of course, since there's nothing breaking out of it in this example here, it's going to loop forever until you manually break the program. But something interesting here is that break itself isn't a statement. Break is actually an expression, so we can return a value from it. So we can say break and then the value that we want to return at that time. So let's try this example out. We'll create a new mutable counter object, set it initially to 0, and then we're going to create a result variable, which is going to be equal to the output of the loop. So the first thing we're going to do in this loop is increment the counter, and then we're going to check to see if the counter is equal to 10. If so, we're going to break out of the loop and return the result of the counter times 2. Okay, and then we close off these brackets here. And keep in mind that since this entire thing is a let statement, it all needs to end with a semicolon here. Let's run it. And of course I have a typo, actually a couple of typos, which you were likely complaining about through the screen, which if so, I appreciate you trying to let me know. All right, so that ran and we get the result 20. Pretty nice. Now it does introduce something kind of interesting, but also a little weird, which is the concept of loop labels, which is a way to effectively name a loop. So if you have nested loops, you can break out of a higher level scope from a lower level loop, which I can definitely see some utility there, but may also be decently confusing. And since this example is so large, let's actually just modify our branches example to contain this code. And here we go. We have 2 loops here. The first one named counting up, and the second one doesn't have a name. So when we reach this condition here to see if count is equal to 2, we're going to break out of this outer loop. I was pretty confused to see this notation here, what we're using for a label. So my curiosity got the better of me, and this notation may have something to do with what's known as lifetime. Now, I didn't want to spoil too much for myself at that point, so I left it there. Just know that loop labeling is a thing and may come in handy if you need to break out of a nested loop structure. And if we run that, we see that we get the following output. Now, other loops we may be familiar with if we're coming from other languages is a while loop, which is going to loop while some condition is true. Remember that this is going to be a Boolean check here. So until this statement is false, it's going to execute the code that happens within the code block. And then the final looping mechanism covered here that I'm really glad that Rust has is for loops, because I really am a fan of them. And I use them for at least 90% of loops that I do. Now, what they talk about here is that for loops can be used over elements of a collection. So I'm thinking that collections must be similar to some type of iterable or iterator like we have in Python. And the way that this works is pretty much how we'd expect it to. So if we use their example here and create a new array, it will say just equal to values 1 through 9, and then we iterate over those. So for num in my array, then we're going to do something. And what we can do is something simple like that. I guess I should make sure that I'm running that as a macro. And here we go. Num is equal to 1 through 9. Now, something interesting here, which I was kind of assuming based on what we saw with loops and that this did not end with a semicolon, is that I think for loops are also expressions. So we could likely get a value out of that. So what if we were to do this? So after our print line statement, we're going to have the last value in the for loop be the number itself. And then we can try to say let max equal to, and then this would be the last number that comes out of the for loop. So let's see if that works, and it didn't. So maybe it wasn't what I was hoping. I may play around with that a bit more, but if you know if there's any kind of magic that you can do with for loops and the fact that it's not a pure statement, let me know in the comments because I'm really interested in that. Okay, let's start the final quiz. And we need to check to see if this code is going to loop forever or not. And we have a couple of nested loops here. So instead of reading through this, instead of reading this aloud, I'm gonna look through it and try to reason through some things. So we're starting with x being equal to 0, and that's a mutable variable. Okay, so we're gonna increment x in the A loop by 1 each time. And then the B loop, we're gonna check to see if x is greater than 10. If so, we're gonna continue the loop. Otherwise, we're going to break the loop. So B should break for the first number of times that A loops, but at the end of A's loop here, we also have a break. So it looks like it's going to break pretty quickly. So I'm going to say that it is going to terminate. Now we need to see if this is going to pass the compiler, and if it passes, write the expected output. So we're creating a new array, length of 10, the seeded values of 5. We're going to have a mutable sum variable here. Then we're going to iterate over A and add the values onto that. So I'm not seeing anything immediate that would stop it from compiling. Since sum is starting at 0, we should have 5 times 10. So I'm just going to say that 50 is the output here. Okay, so we were correct about question 1, and it says that it'll terminate after the first iteration of the loop because of that break statement there. Okay, good. And then question 2, yeah, we're correct for both. Fantastic. So that brings us to the end of this chapter and the end of this video. Thank you for following along with me. This journey into Rust has already been pretty interesting, and I'm really looking forward to seeing what the rest of the chapters of this series are going to result in. If there's anything that you found confusing or even interesting about what was covered in this video, please let me know in the comments and we'll have a discussion about it. But until next time, thanks for watching.